All right, let's move on. The material basic coverage ended last Wednesday. We continued on with new materials Friday and today, but that material won't be on the exam. Will not be on the test. All right, so the question we're going to look at today is an algorithm for determining stability. So the question that we want to look at today is this system stable? And the system, so in the abstract sense, I have this idea. This is the output. This is the input. And we have a model of called the transfer function. And the thing that we know from system theory is that the system is stable if and only if something happens. So G of S describes a bounded input, bounded output, stable system. Double arrows means if and only if. G of S has no poles in the right half plane. Okay, no poles in the right half plane. So some very simple examples. Let's do just a few examples just to illustrate what I mean by this. What we gotta do is we had to focus on the denominator, and we say that the roots, the pole, this one has a pole at s equal to -2. That's okay. Okay, this is a system where there are poles and zeros, but we focus only on the bottom. Focus here. The top does affect the response, but it doesn't cause it to either blow up or decay. Whether or not the system blows up or decays is determined by the roots in the denominator. So this is all review of something we have covered already. So this could be on the exam. This is just backing up, just kind of reviewing again. Okay, pole's at -3. That one's okay. Okay, and the last example is that of an unstable system. So tools that would be helpful for us, if we know the model, we need, like in MATLAB, we could use this command, roots of 1, 2. Okay, this describes like s plus 2. It's just finding the roots of a polynomial. So this is in MATLAB. You won't have MATLAB available on your calculator. I'm told you can get it on your cell phone.
That's cool.
But you won't be able to use your cell phone on Wednesday. Question in the back.
Will MATLAB applications be on the exam? Like, will we need to know commands for MATLAB?
Will you need to know? The question is, will you need to know commands from MATLAB? That's a great idea.
Why would you do that? Please don't.
You look at some old exams. There have been exams with MATLAB. All right. This is not MATLAB. This is your calculator. You're going to need some sort of root solver.
That would be 20. That's supposed to-
Okay, and I cannot help you with that. Simply because I don't own a calculator anymore. All right, so work with each other, figure out how your TI-98 solves roots. Make sure you put it in complex mode. Okay, now what we're going to look at today, however, is this problem. So I'll give a sometimes in a system we have things that are adjustable. So the idea is here I have two constants or two gains, gamma 0 and gamma 1. They're adjustable. And so since we don't have numbers, we can't plug that into our calculator. And so what we want to know is maybe what ranges of gamma 0 and gamma 1 yield a stable model. So this problem is a little bit more difficult to deal with. Okay, we know we have to focus on this part, but we cannot enter variables into calculator. We have to enter numbers. Right? Now it turns out that there is an algorithm for determining how many poles there are in the right half plane. Fortunately, there is an algorithm to determine the number of roots of a polynomial in the right half plane. There's an algorithm to determine how many poles there are in the right half plane. We want it to be 0. All right, so that algorithm is what we're going to cover today. That's our today's focus. And so this is called the Routh-Hurwitz criterion. Okay? Ruth Hurwitz. Okay, it's the Routh-Hurwitz criterion. So what we do is we take the denominator polynomial like so. Okay, so there's a bunch of coefficients. I'm going to call these A's, like so. And what we do is we'll construct an array. Okay, and this is what the array looks like. This is an nth order polynomial, n is a number, so we first make a list of all the rows that are going to be in the array. We do this, s to the n minus 1, continue on down. The last one will be s, and then the last one, well, this is s to the 1, and then s to the 0 is just equal to 1. Okay. So we just make a list like that. These are going to be rows of information that we got to put in. Now we're going to build this array. And the way we start the array is we take these coefficients, and these coefficients go in the first rows. They go in the first 2 rows. Okay. And they go in this way. This coefficient here is a 1. Okay, this is a 1. If it's not a 1, you can put in some other number. But for this example, I'm just putting in a 1. So it goes 1, an minus 1, an minus 2, an minus 3, an minus 4, and so forth. Okay, so you're just listing them, kind of zigzagging down like so. Okay, and just list them. Then what we got to do is we got to fill in the rest of the arrays. So the coefficients in this row, I'm going to call b's. I'm going to call this one b0. Call this one b1. And then this row has got some coefficients. I'm going to call this one c0 and call this one c1 and so forth. Okay? So I'm going to write down the formulas for the b's and the c's, and then that will give us a pattern for what all the rest of the coefficients will be, and then we'll do some examples. Okay, let's take a look at B0. The way we construct B0 is 1, an minus 1, an minus 2, an minus 3. We'll take that 2 by 2 determinant, we'll put a minus sign on it, and then we'll divide by an minus 1. So basically, I've taken this set of coefficients right here. So I'm working on B0, so I take this set of coefficients right here. And I make this array. I got to find the 2 by 2 determinant, put a minus sign in front of it, and then divide by this number right here. Let me show you B1. B1 is also a 2 by 2 array. You keep the first column, 1, an minus 1. That doesn't change. All right. So basically, this part doesn't change. We use this part. That doesn't change. It's right here and right here. Don't change that. What changes is the next column. So for B0, we used this column of numbers, and it came right here. For B1, we'll use this set of numbers. And so I'll have an minus 4, an minus 5, and then we divide by an minus 1. This also does not change. This comes from right here. That does not change. So the only thing that changes in this Rouse array calculation is the second column. All right? We repeat. After we get these done, we repeat and do the same thing, a similar sort of thing with C's. Let's take a look at what are the equations for the C's. So I'm going to fold the B's out of the way, and we'll write equations for the C's. We need to do a 2 by 2 determinant, put a minus sign in front of it. We're going to use these 4 coefficients. And so it'll be an minus 1, b0, an minus 3, b1. Okay. Similar sort of pattern as we did before. We take the 2 numbers above. They form the first column. This first column will not change for any of the C's. Then we'll take the next set of coefficients in the next column and stick them in here to form these. And then we're going to divide now by B0. Okay, let's do C1. It's 2 by 2 determinant again. The first column doesn't change. Should be this, an minus 1, B0. We've already used these 2 coefficients here, so we got to do the next coefficient over. I didn't write them down, but we can kind of guess what they are. This one is going to be an minus 5, And this one is going to be B2. And then we're going to divide by B0 again. Okay, let me zoom out a little bit so we can see if we can get everything all on one screen, maybe. That's constructing Routh's array. I'll leave that up there a second. Okay, take your polynomial. It's got a bunch of coefficients. In my example here, the first coefficient is 1. If it's not a 1 in your example, you just need to carry it along. And then just start populating this array. First 2 rows. Up and down. Until you get them all finished. Then you calculate all these coefficients. They involve 2 by 2 determinants. And then a scalar. Now, once the array is done, what we do is we focus our attention on the first column of coefficients. Okay, can I go on? We'll do an example. But it's kind of like the whole lecture is kind of, the theory is on this slide right now. Let's go on and let me state what is Routh's criterion. Okay, what does the criterion say? The criterion says number of roots in the right half plane is going to be equal to number of sign changes. Number of sign changes in the leftmost, in other words, the first column of coefficients. Okay, so we're going to build this array. The array looks like right here. And what we're going to do is we're going to focus our attention on this column right there. We've got to calculate the whole array. We need the whole array so that we can calculate all these coefficients. But then what we're going to do is we're going to say, what's going on in the first column? And we'll have to see how many sign changes there are. So in this example, this is a positive number. And then I see if there's a change. So I say plus, 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 plus. If they're all positive numbers, there are no sign changes. That means the polynomial has no roots in the right half plane. And so the system will be stable. If there's a sign change, let's suppose this is a minus sign, then and the rest are all positive, then I would say plus minus is 1 change, minus the plus is 2 changes, plus, 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 plus. So there would be 2 sign changes, and so that would tell me that there are 2 roots in the right half plane, and the system is unstable. So that's Routh's stability criterion. Number of roots in the right half plane equals the number of sign changes in the leftmost, or the first column of coefficients. All right, let's do an example. What range of k yields a stable system? Okay, that's the question that we have, and the model is this. Some stuff in the numerator, we don't care. We need to focus our attention on the denominator. I tell you what, we have too many threes floating around. It's going to be a little bit difficult for us to figure out which three we're dealing with. So I'm going to change the numbers here. Let's make this one a 4 and make this one a 5. Okay. Okay, so let me construct my array. Okay, it's a third order polynomial. So I got to list 4 rows. S cubed, S squared, S to the 1, and S 0. So then I list my coefficients. 1, 4, 5, K. K is the variable. Okay. And then I got to calculate B0, B1, C0. C1. All right, let's see if we can squeeze everything in here. Let's do B0. I'm going to just do the scratch work over here. B0 is equal to a 2 by 2 determinant, and I need the numbers 1, 4, 5, and K, and I got to divide by 4. Okay, do we remember how to do a 2 by 2 determinant? This times this minus this times this, right? But then you got a minus sign. So the other way to do it is to say, if I don't want to do the minus sign, I got to do the determinant kind of backwards. And so the answer is 20 minus K over 4. Okay. Any questions on doing the 2 by 2 determinant? Next, I got to do B1. B1 is the determinant formed by, first column doesn't change, formed by 1, 4, first column doesn't change. Next, I got to take the coefficients over here. They are 0 and 0, and then I divide by 4. So that number is a 0. Let's do C0. C0 is a 2 by 2 determinant formed by, here's C0. I got to take these digits, 4, B0, K, B1, divided by B0. Somebody said just K. Okay, I was debating whether or not I need to carry out the algebra, but especially since it's Monday, and you all are sharper than the
Isn't it
bunch that I have.
Isn't it negative K?
Let's have a little discussion. Is it K or negative K?
K.
Okay?
Okay.
Is it okay?
I'm done.
No, it's Monday. Look at all. All right, so let me clean up the array, this completed array, and okay, there it is. I took the zeros out. Now, let me give you a little sanity check. Study the even rows. Odd row, even row. Odd row, even row. Even row, last term. Okay. Even row, last term. Notice that it's the same. So if we've done our math correctly, this is an algebra check, these better all be the same. Now for those of us who do this type of calculation a lot, this is not a sanity check anymore, it becomes a shortcut. Rather than calculating, we just know, the last elements ought to be the same, and so we just fill it in that way. All right, so now our question is, we've got to focus on this row, okay? This is the completed row that we've done the sanity check, and now what we're going to do is we're going to study the set of coefficients. For a system to be stable, we must have no sign changes here. So, positive, positive, positive. This has to be positive. So we get the conclusion that 20 minus k must be greater than 0. And we also get that this has to be positive. K must be greater than 0. So our conclusion is that k has to be between 0 and 20.
Not greater than or equal to? Or does 0 count as not negative or positive?
Okay, so the question is, positive, positive, how about 0? Is 0 negative or positive?
Neither.
It's neither. This kind of goes back to the question of, is a pole on the imaginary axis, is that stable or unstable? I made the joke, would you want to go out with a person whose margin is stable? And the answer is no. So, yeah, the stability boundary is k equal to 0, k equal to 20. You're on the verge of instability. Okay. If you write some English words, just kind of say something to that effect, then it indicates to me that you understand what's going on here. All right. Do we need another example? We are moving along quickly here. Do we need another example? Yes, question.
Does k have to be greater than 0? Like, how do we know it has to be?
Okay, so the question is, how do I know k has to be greater than 0? The criterion says that the number of poles in the right half plane is equal to the number of sign changes. That means, say if this was a negative number, everything better be a negative number. I'm looking at sign changes. So this was positive, positive, this has to be positive, and this also has to be positive. So from this, I came to the idea that k has to be greater than 0, because everything has to be positive.
For it to be stable, right?
For there to be no sign changes. No sign changes means that there will be no poles in the right half plane, and they will be stable.
Okay.
So if you had a 1 and then -4, how would that change k?
If this was a -4, you don't need to go any farther.
Oh,
If this is a -4, that'd be 1, it's positive. -4, that's a sign change. Playing with k is not going to affect it. You're always going to have at least one sign change here. It's an unstable system.
oh.
So there's no math in that. Okay. If you've got a term that's missing, suppose this was not a 4, this was a 0.
Marginally stable.
It's as good as unstable. Okay? So you don't have to go any further. There's these little algebra shortcuts you discover. Where if I'm missing coefficients, that's bad. If I have coefficients that have changed sign, that's bad. Okay, not changing sign doesn't mean that things are necessarily stable. I mean, you could have all positive coefficients, but that doesn't mean it's coefficients in the polynomial, not coefficients in the column. Okay, this problem's a little bit more difficult because now I've given a model that's. We start off our discussion with saying, is this system stable? Is this system stable? I just draw a block. And I say we need to study the denominator of this system. But now I don't tell you what the denominator of the system is. I give you some pieces. And now you have to find the model of the system. So first, find y of s over r of s. So we have to use what we know about feedback system models. So forward gain from r to y is going to be k s plus 4 s minus 1, s minus 2, divided by 1 minus the loop gain. The loop gain is the gain all the way around the loop. In this case, it's k times s plus 4 over s minus 1, s minus 2, and there's a minus sign here, it turns this minus sign into a plus sign. Let's clean out the algebra a little bit. I get k s plus 4 on the top, and on the bottom I get s minus 1, s minus 2, plus k s plus 4. Okay. Now leave that up there a few seconds, let you figure out how I did the algebra.
Would you be okay with us programming our calculators to do it?
So the question is, would I be okay with y'all programming your calculator to do it? I would be amazed and delighted if you could do something like that. But it's your calculator. So you're allowed a sheet of notes and your calculator. Any magic you can do on your calculators on the table. Okay? It's far and above my capability.
Our Wi-Fi enabled calculators now, right?
He said, you know that there are Wi-Fi enabled calculators, right? Yes. I've been apprised of that, and I've decided that I will retire before trying to solve that problem. Any discussion about this result up to this point? Concerns? Okay. We need to focus our attention on the bottom. Yes, there's stuff on the top. Yes, it affects the response. It makes it slightly bigger or smaller in certain parts of time, but it doesn't cause the system to blow up. What causes the system to blow up or decay are the roots of this. And so let's take a look and see what we have here. So let's clean this up. Focus here. Okay. In system theory, we call this the characteristic polynomial. Characteristic in calculus, we have a characteristic equation. The character or nature of it is determined by this stuff in the denominator. So let's focus there. I'm going to slide that up here, and then let's clean that up a little bit. S minus 1, S plus minus 2, plus K S plus 4. This is the same thing as S squared minus 3S plus 2 plus KS plus 4K. So I have S squared, I got a 3S and a KS, that's a K minus 3S, and then I have a 2 plus 4K. Just cleaning up the algebra of the denominator. This is called the characteristic polynomial. You might remember that word from calculus. Characteristic polynomial. It's the denominator. Okay. All right, now let's do Rouse array. We got this coefficient, and this coefficient. Let's do Rouse array. S squared, S1, S to the 0. 1, K minus 3, 2 plus 4K. This is a 0. Okay, it's a 0. This is B0. B0, just practicing the calculation, is 1k minus 3, 2 plus 4k, and a 0, divided by k minus 3. And we all know now that that answer is 2 plus 4k, if we've done our algebra correctly. Because it is the last element in an even row, and it will match this. Okay. So for now, if you're doing homework, I would recommend you go ahead and do this calculation, just so you kind of get a feel for where the coefficients fall. But as you become practice, you can use this as a quick shortcut to say, oh, last element in the even row, it better be somewhere in this row. Now, where is it? Is it here or is it here? That comes with a little bit of practice. You'll discover where it needs to go. All right, so let's take a look at the first column. We're going to focus on this first column right here. So let me write that up. Okay. If I want a stable system, I want no poles in right half plane, means I have no sign changes, which means that k minus 3 has to be greater than 0, and 2 minus 4k has to be greater than 0.
I'm sorry, I think that's 2 plus 4k.
2 plus 4k?
Yeah.
Yeah, sorry, thank you. 2 plus 4k. So, what do we get here?
Is greater than -1/2.
I get, from first one, I get k is greater than 3, and from this one, k has to be bigger than -1/2. So, what does that mean? If this is k, this is 0, this is -1/2. So one of the things says it needs to be greater than -1/2, and the other one says it has to be bigger than 3. So the answer is k better be bigger than 3. K being greater than 1/2 is not enough, -1/2, because it won't satisfy this. All conditions have to be satisfied. It's an AND condition. So the only condition that satisfies all, assuming I haven't made any algebra errors here, is k greater than 3. Any questions? Okay, seeing none, I suggest we stop.